Hello students, welcome to the video class for the subject Power Electronics and PLC. This subject is for 5th semester Electrical and Electronics Diploma Engineering students. So today's topic is your factors affecting speed of DC motor, and speed control of DC shunt motor using converter. Okay, so in the previous part we already discussed about the converter circuit. Okay, we studied different types of converter circuit like half bridge, full bridge. Okay, so half wave controlled or full wave controlled. So here we are using controlled rectifier circuit for the control of speed of DC shunt motor. And about the DC shunt motor you already studied in your previous semesters. Okay, so we will not discuss here about the features of the DC shunt motor. We just focus on the points whatever you read in the previous semesters, and by using those key points you are studying about the speed control of DC shunt motor using converter. So let's focus on the first point, that is the different factors affecting upon the speed of DC shunt motor. Okay, so see this equation, EB is the back EMF. This equation is phi Zn by 60 into P by A. So we know that the back EMF, this is the generated EMF in case of DC motor, is the P phi Nz by 60A, where phi is the flux per pole, then P is the number of poles, A is the number of parallel path in the armature, Z is the number of conductor, N is the revolution per minute. So from this equation we can find out the N is, so here N is the armature rotation in revolution per minute, or it is also in revolution per second. So here basically this N represents your speed. So from equation 1 we can find out N is equal to 60 EB into A divided by P, Z and phi. So from this, see here in this case, in case of DC motor, your number of pole is constant, then number of parallel path in armature, this A is also constant, this Z, number of conductor is also constant. So here 60 constant, here A constant, P constant, Z constant. Okay, so the left out part is we replace all these things in as a N is equal to K is a constant, into EB by phi. Here EB is not constant and phi is not constant, and the rest part are constant. So we represent all the constant term as K. So N is equal to K EB by phi. So where K is the your 60A by PZ. Okay, so this is a proportional constant. So this equation, so that this from this equation 2 you can write that speed proportional to EB and speed inversely proportional to phi. That means speed depends upon now two parameters, that is the back EMF and another one is phi, flux per pole. So here EB is also can be expressed as, in case of motor, in case of DC, that EB is equal to V minus IaRa. Okay, this is also another equation in terms of armature current, armature resistance, and terminal voltage. So from this equation here, see, we found out that EB is proportional to directly proportional to speed, and speed is also inversely proportional to phi. So we can write in place of EB N phi. Okay, so N phi is equal to V minus IaRa. See, N is proportional to EB by phi. So from this we find out that EB proportional to N phi. So here N phi is written in place of EB. So N phi is equal to B minus IRA. So here N is equal to B minus IRA by phi. Okay. So see here we also seen that N is again depend upon in the upper cases. In the upper cases N is depend upon back EMF and N is depend upon the flux. Okay. Because field current is not constant, so that's why flux is also not constant term, it is a variable term. Okay, so see here, speed is from this equation, from this expression, speed is directly proportional to V and speed is inversely proportional to IA. Okay, so here overall speed of a DC motor depend upon back EMF, field flux, armature current and supply voltage. So these are the four parameters on which speed depends upon. So if we need to speed control above the base or related speed, then we have to do flux control method. But if we need to speed control below the base speed or rated speed, then armature control method is required. Okay, so we need to control the speed, so by using the flux control method we can control the speed. But if we need to control the speed below the base speed or rated speed, okay, so by the flux control method we can control the speed above the base speed. But if we need to control the speed below the base speed or related speed, we have to use the armature control method. Okay, so the next part is the speed control of DC shunt motor using converter circuit. So the basic part you understood about the different parameters on which speed depends on in DC motor. So in case of DC shunt motor, how we speed control? We control the speed by using converter circuit. Let's see. We know that DC shunt motor is a constant flux motor like separately excited DC motor. In case of DC shunt motor, here is a constant flux motor. It is like a constant flux motor, like a separately excited DC motor. So speed control method for DC shunt motor is very similar to speed control of separately excited DC series motor. So let's take a single phase full wave converter for the control of speed of DC shunt motor by using armature voltage control method, which is given below. See, this is the single phase full wave converter. Single phase full wave converter I already told you in the rectifier or converter subject part, converter chapter. This is the AC supply, this is the bridge, this is the converter circuit connected in bridge form. 4 thyristors T1, T2, T3, T4 are connected in bridge form. Then this is this part is the your shunt motor. Here you have this is the shunt field. Okay, this is the armature. In the armature, this is the armature resistance, then armature inductance. This is here also RSS is the shunt field resistance, LSS is the shunt field inductance. This is EB back EMF. So this is the circuit diagram. So here V is equal to supply voltage, V is equal to V max sin omega t. So here 4 thyristors are used for control the speed of DC motor. So at a time only 2 thyristors are operated. So first is the mode 1. So in mode 1, first we consider the positive half cycle. So when a positive half cycle is given, then thyristor T1, T2 are conducted. Already I told you it is like a full wave control. So when this is positive half cycle means this is positive, this is negative. So current will flow like this. This is the path. See, this is one current, this is another current. Divided into 2 parts and again through this path return back to the minus term. Okay, so you got one current here, you got one current here. This total current is outgoing and reach here. Okay, So this is your current conduction path. Okay, so see what happens. So in the positive half cycle, thyristor T1 T2 are conducted with providing gate poles simultaneously, so that the current flows through armature winding as well as field winding. So new, this is the armature winding, this is the field winding. So but the armature current is controlled by with external resistance. Similarly, the field current is controlled by using the external resistance their own. Okay, so for this mode, the current path is, I told you, supply voltage, then thyristor T1, then armature and field winding, then thyristor T2, then Vs minus. Okay, in mode 2, for negative half cycle, thyristor T1 T2 reverse biased and T3 T4 are forward biased, and give T3 T4 are forward biased, and when we give the gate poles simultaneously, then they are operated, and again the current pass through both armature winding and field winding, and again the both current values are controlled by their respective external resistance. So here we already seen from any DC motor that speed is the V minus IaRa by phi. This we found here. Speed is equal to, this is V minus IaRa by phi. Okay. So here I wrote here, speed is equal to V minus IaRa by phi is equal to, if we split this expression, V by phi minus IaRa by phi. Okay. So here torque proportional to Ia phi. So actually for shunt motor, torque is proportional to phi Ia. So if we put this expression, Ia proportional to torque by phi. Here we found Ia expression. Okay, this Ia expression is put here, this in this part. So speed is equal to V by phi minus Ra into T Ea by phi square. Okay, so this Ia expression is changed here, replaced here, and from this expression, speed is proportional to V by phi minus Ra into T Ea by phi square. So for continuous conduction mode, okay, for continuous conduction mode, your Va is equal to 1 by pi integration alpha to pi plus alpha V max sin omega t d omega t. This gives to V max by phi into cos alpha, and from here we have found the average output voltage. This is the 2V max by pi into cos alpha. Okay, so that see here, speed is equal to V minus phi minus V by phi minus Ra Tea by phi square. So for any DC motor, but for DC shunt motor, phi is constant. Okay, phi is constant. So see here, V is equal to, constant means V by K. K is the constant, minus Ia minus Ra into Ta by phi is also constant. So K square. So from this we found N is equal to, see, V is this V is your our DC voltage which is given input to the DC motor, and this DC voltage is the output of the rectifier circuit, and output of rectifier circuit is this VA, this average output voltage, average output DC voltage. So this expression is put here. So speed is equal to 2V max by K pi into cos alpha minus Ra Tea by K square. Okay, so see what we found here, that if alpha lies in between, when alpha lies in between, see what happens here. In this expression, speed is equal to this 2V max, V max is constant here, K is constant, pi is constant, cos alpha, this alpha is the delay angle, and Ra is also constant, T torque value and K, these are all constant terms. So here only the parameter, that is alpha, that is the delay angle, firing angle at which the speed is dependent. So if alpha lies between 0 to 90 degree, then the speed of the DC shunt motor speed is equal to V max by K only. And if this alpha lies between 90 degree to 180 degree, then the speed of DC shunt motor is equal to V max sin alpha by K. Okay, so here our speed is depend on the alpha, delay angle or firing angle. So let's take 2B max by pi is equal to maximum average terminal voltage of DC shunt motor. This voltage value equal to rated terminal supply voltage. Okay, so let's take 2B max by pi is equal to 2B max by pi means this part, 2B max by pi. Okay, so let's take 2B max by pi is equal to maximum average terminal voltage of DC shunt motor. This voltage value equal to rated terminal supply voltage. Okay, so this is the wave diagram waveform. See, this is the supply voltage, this is the maximum V max level, this is alpha angle. So at this alpha angle we give gate pulse, gate current is given here. So after giving gate pulse, this is the output waveform we have found. This is the output waveform, this is the EB level, back EMF level, and this is the V max level. Okay, so this is the continuous conduction mode we are studying. So this is, that's why here current is like this. Okay, so due to the presence of inductance in the load, so here load is our DC shunt motor, and in the DC shunt motor there is a field inductance, armature inductance, and due to the presence of inductance the current waveform is like this. Okay, and the voltage is like this. This is our voltage. Okay, this is our voltage, and like this you found the voltage expression, voltage waveform and current waveform. Clear? This is our continuous conduction mode. Okay, so this is all about your speed control of DC shunt motor using converter. Okay, thank you.